How OSPF is configured is relatively simple, but how it operates in the background is a little bit more complex. Understanding how it operates in the background will help you configure it properly and troubleshoot it more easily. That's what this video will go through, is how OSPF operates. There are 7 different states in which OSPF transitions through, and we'll talk about all 7 of these states in this video. Initially, when an OSPF router connects to its networks, the first thing it's going to try to do is create adjacencies with its neighbors. It's going to send out hello messages and try to find out who its directly connected neighbors are. It will then try to exchange routing information with those neighbors, calculate the best routes available, put those in its routing table, and reach a state of convergence in which it has consistent link state databases and routing table information with everyone else in the OSPF domain. So we'll start this off in the down state. Initially, an OSPF router interface or a link is in the down state. Essentially here nothing has happened. We haven't sent out any hello messages and we have not exchanged any information. So OSPF router is going to be in this state initially when it first starts up, or if it has not received a hello message from its neighbor within the dead interval, which is typically going to be 40 seconds. So if he has not received a message from his neighbor in 40 seconds, he can transition back to this down state. You can see that the example that we'll be using has 2 routers, router A and router B. You can see that we have loopback interfaces configured. This is the way we want to properly set up OSPF, is to configure loopback interfaces. Those will become our router IDs, as we have not explicitly set them. You can see here that we have no neighbors, we're in area 0, and that we're both in the down state. Next, we'll transition to the init state. An OSPF router will attempt to form an adjacency with its neighbor by sending out a hello message. So when it very first sends out its first hello message, it is now in the init state. So router B starts off the process by sending a hello message over to router A. You can see here we transition into the init state. Nothing else has changed. In that hello message, you can see that the source address is coming from the fast Ethernet of 192.168.1.2. The destination is the multicast address of all SPF routers, 224.0.0.5. You can see here that we're in area 0. You can see how they denote area 0 by the 0.0.0.0, also listed as the backbone. There must be an area 0. You can see that the hello interval is 10 seconds. The dead interval is 40 seconds. There is no DR or BDR at this point in time. One thing to note, in order to form an adjacency with router A's hello and dead interval would have to match that 10 and 40 seconds. So when a router receives a hello, it will add the neighbor's router ID to its list of neighbors. So router B sent over hello to router A. When router A gets that message, he transitions to the init state as well, and he also adds router B as a neighbor. 192.168.31.22 lists him as a neighbor in his table. So we're going to transition to that init state when we either send a hello message or we receive a hello message. What router A and router B want to transition to next is the two-way state. And the way in which it transitions to the two-way state is when it gets a hello message with himself listed as a neighbor ID. Essentially, we're looking for some confirmation that someone has us listed as a neighbor. So now what's going to happen here is router A is going to send over his hello message, and in his hello message we will see that we have a neighbor ID of router B. So when router B gets this hello packet, this is what it looks like, coming from 192.168.1.1, that's coming from the fast Ethernet, going to the all SPF routers address. You can see here again that we're in area 0. What has changed though is an active neighbor, 192.168.31.22. So router A is saying over to router B, I have a neighbor, 31.22, that is you. When router B sees himself listed as an active neighbor coming from A, he can now transition to the two-way state. So once a router receives a hello packet and sees its own ID in the neighbor field, the router transitions to the two-way state. And what the two-way state indicates is bidirectional communication is established. To complete this handshake here, router A needs to see himself confirmed from a hello packet as a neighbor in the neighbor ID field from router B. So router B is going to send over a hello, and in that message he will have a neighbor listed of 192.168.31.11, which is router A's address. So router A will get that packet, see himself listed as a neighbor for router B. He will transition to the two-way state as well. So here they are, both in the two-way state. They both have each other's neighbors listed, and they have bidirectional communication. Keep in mind that this process would have to happen for every neighbor that router A and router B has. This here is just illustrating the relationship being formed between A and B. So essentially what we've done here is what's inside of the tan box. We've established our neighbor adjacencies. We went from the down state into the init state by sending or receiving a hello message, and then we transitioned to the two-way state by receiving our ID back. The next steps are going to depend on which type of network interface that we're a part of. In a point-to-point network, we can transition right to the exchange start state and start to exchange routers, because on a point-to-point link we only have one other neighbor and one other router to start exchanging routes with. In a multi-access network like Ethernet or frame relay, let's pretend that we have 4 or 5 routers plugged into a central switch, then we must elect what's called a DR and a BDR, or a designated router and a backup designated router, before we can begin exchanging routes. So as I said, we must select a DR and a BDR in multi-access networks so that we can reduce our routing update traffic. Essentially how a DR and BDR works is when a router identifies a change on a link, for example, a link connected to this network going down, he would just inform the DR, and the DR would then let everybody else know. If we did not have the DR and BDR, what would happen is this router would let this router know, which in turn would let this router know, which in turn would let this router know, which in turn would let this router know, and then these routers would in turn let their neighbors know. We'd end up flooding around the same exact information from router to router to router, using up vital bandwidth and causing a lot of inefficiency. So instead what we can do is just let the DR and the BDR know of that change, and they can let everybody else know instead of having to flood that information from neighbor to neighbor to neighbor. If you wanted to figure out the number of adjacencies that you would have to make without having a DR and a BDR, what you do is you take the number of routers that you have times the number of routers that you have minus 1 divided by 2. So in this example here we have 5 routers. 5 times 5 minus 1, which is 4, so 5 times 4 is 20, divided by 2 is 10 adjacencies. So every single router would have to form 10 adjacencies, and they would then essentially be sending that information to 10 different routers instead of just informing only the DR and the BDR. We typically want our DR and our BDR to be our more powerful routers. The DR and the BDR will have to process more link state advertisements than the average router. Because of this, we typically want to try to rig the election and not leave it to chance. So a DR and a BDR are going to be elected for every multi-access network using their hello packets as ballots. Who will end up winning the DR election is the router with the highest router ID. Remember, our router ID is either going to be explicitly set, it's going to be our loopback interface, which we typically want to set, or it will default back to the fast Ethernet. The proper way in which we can ensure that the router that we want to become the DR or the BDR is to set the OSPF priority. The OSPF priority command will take precedence over the router ID. By default, the priority is 1 on every router, and the highest router ID breaks any tie. So that is why the router ID is used to elect the DR and the BDR by default if we do not change the OSPF priority. If we took a look down here at this middle segment, the 10.5.0.2 is the fast Ethernet address on router B. That is higher than the 10.5.0.1 address over here on router A. So since we did not set a router ID with a loopback or explicitly, and we did not set the priority, this router B will become the designated router. In addition to electing the designated router, we also elect the BDR. The BDR is the router that takes second place in the election. And the BDR is used in case the DR happens to fail. So if the designated router fails, the backup designated router kicks in and takes over. It's kind of like a president and vice president scenario. If the president died, the vice president takes over his duties. If the designated router goes down or fails, the backup designated router takes over its duties. We would then hold a new election for the backup designated router. One thing to note is that once you are elected the DR or the BDR, you will remain in that role essentially forever until that OSPF process is restarted or until the routers are rebooted. So even if you added a router with a better ID or a better priority, it is not going to overtake a role. It is going to have to wait its turn. I'll show you an example of what I mean by that. Let's pretend that we had 3 different routers all connected to a central switch. So we have a multi-access network here. And with the multi-access network, we must elect the DR and the BDR. I'll put in some router IDs that I explicitly set for each router. In this scenario here, without setting priorities, this router down here would become my DR because it has the highest router ID. And this one here would become my BDR because it has the second highest router ID. In the event that this router here fails, what's going to happen is he will become our new DR. We will hold an election for a new BDR, and this is the only router left, so he is the BDR over here. If this router came back up and on, he would not take over the DR role. Essentially what he would have to do is wait his turn. So now this is the DR and this is the BDR. If this happens to fail, this would take over and become the designated router. He's back up and running. We would hold a new election for the backup designated router. He would win that. He is now our BDR, even though he has a router ID that's higher than everyone else. If I do this with priorities, it does not matter what the IDs are. So let me add in some priorities in here. Let's pretend that I add this with the priority of 0. I'll add this one with the priority of 255, which is the greatest, and this one with the priority of 100. What a priority of 0 does for you is it takes you out of the election. It essentially says, I do not want to be involved in this election. So this router here will never become a DR or a BDR. So here when they hold the election, this router will end up becoming our DR because the priority is the highest, 255. This router down here has the second highest priority, will end up becoming the BDR. If the DR happens to fail, if this DR goes down, what's going to happen is this will kick in and become our designated router. So the backup designated router kicks in and takes over the DR role. We would hold an election for the BDR, and what we would find out here is that there would not be a BDR because this router is down and this router has a priority of 0. If this router came back up, he would then become the BDR. It would not matter at this point. This is the DR and this is the BDR. If we were to add another router into this mix, the election has already taken place. He cannot overthrow the DR or the BDR. He must wait his turn no matter what his ID is or what his priority is. So once we have our DR and our BDR elected, essentially how this operates is that, again, whenever one of these other routers, also known as a DR other router, finds out that there has been a change to a link, he will send that to the 224.0.0.6 address, which is the all DR routers address. The DR and the BDR listen on that address. So again, instead of letting everybody else know on the network, they just let those two guys know, the DR and the BDR. Then what the DR will do is it will send out the advertisement to the 224.0.0.5 address, which is the all OSPF routers address. All the other routers will listen on that address, get that advertisement about the change, and make the change to their tables. So what that backup designated router essentially does at this point is it listens, but it does not act. It essentially does all of the different functions that the DR does at this point, but it does not flood out the 224.0.0.5 because the DR is responsible for that at this point. So once all routers on a segment agree upon who the DR and the BDR is, they're ready to start synchronizing their link state databases and eventually start building their routing tables. This is the same state that the routers in a point-to-point segment are in already, because on a point-to-point segment we did not have to elect that DR or BDR. So at this point we're ready to transition to our other states. We will start to transition to the exchange start state and the exchange state. Essentially what we're doing in these states is we're exchanging information to build our topology or database table and then start to calculate our routing table. To kick off this process, a master router is chosen and it begins the update process. Once the master router is chosen, we transition to the exchange state. Keep in mind that this has nothing to do with the DR and BDR. We just need one router to start to exchange his link state database information. So we just choose one. I don't expect you to know how that master router is chosen or how it operates. I just want you guys to know that we have to kick off the process of exchanging our database description packets. So we just pick a router known as the master router to start that process. So once we've picked that master router, we're in the exchange state. And in the exchange state, we exchange our database description packets. And this is essentially a summary of everything that we know about. This is a summary of who my neighbors are, who my links are, what networks I'm connected, everything that I currently know about. We'll start to exchange that from one router to the next. And if routers need information about a link or a network, they'll request more information about that until they're all converged or consistent. Remember that all routers in an OSPF area will have identical link state databases. So as we're exchanging these database description packets, there are a few different OSPF packet types that we need to be aware of. We have our database description packets, we have our link state requests, our link state updates, and our link state acknowledgements. So when a router receives a DBD packet from a neighbor, it will look through the link state advertisement headers and essentially look for anything that he does not currently have. If he does not currently have something, like information about a network or a link, it will add that to a link state request list. So he gets a packet. In that packet it talks about networks 192.168.1.0, networks 192.168.2.0, and networks 192.168.3.0. If he realizes he needs more information about that 192.168.3.0, he'll add it to his list, and he'll then ask for more information about that later on. So if a router has entries in its link state request list, he needs more information about that from other routers. What he will then do is he'll send out a link state database request and request more information about that. The router that responds to the request sends out a link state database update, and then they thank each other for that information. If there are no entries in the link state request list, we're ready to transition to the full state, which is essentially what we want to get to in the end. Once we're in the full state, we can start to calculate our routing table. So as I said, if we need additional information about something, we send out an LSR or link state request. The router that has information about that link state request sends out a link state update or an LSU. Once the information that's needed has been received, it will then send an acknowledgement to acknowledge the receipt and thank the router for the update of that information. So after all link state requests have been updated and acknowledged, we are now in the full state. So in the full state, we all have identical link state databases. All routers have exchanged information for all needed links, and our link state databases are identical in every single router. So as I said, the next step is to run through and calculate the routing table. How we calculate the routing table is to run through Dijkstra's algorithm. We take a look at the costs of our links, and whatever has the lowest cost to get from one destination to the next will be input into the routing table. Remember that there can be multiple ways to get from one network to the next, but only the best one gets put into the routing table. All routes to a destination will be remembered in the topology table, but only the best one, based upon the metric or the cost, gets put into that routing table. So we now have successfully transitioned through all 7 of those states. We start at the down state where no information had been sent. Then we send our hellos or receive our hellos and transition to the init state. Once we receive confirmation that we're listed as a neighbor, we transition to the two-way state. We will then elect a DR and a BDR if we are in a multi-access segment, and transition to the exchange start state. In the exchange start state, we choose a master router. That master router will then kick off the exchange state, in which we start to exchange our database description packets. During the exchange of the database description packets, we create a list of any information that we need. And during the loading state, we gather that information that we're missing and update our link state databases so that they're consistent with all other routers in that OSPF area. After they're consistent with all other routers, we are now in the full state, ready to run through Dijkstra's algorithm, calculate and put the best routes into the routing table. That's all for this video on OSPF Operation. Thanks for watching.